In this section, we're going to look at empirical and theoretical probability, and we need to go over some terminology before we begin to make sure that we are on the same page, acknowledging different vocabulary words and using them properly. So the first word we need to know and understand is what is an experiment. It's a controlled operation that yields a set of results. If you think about it, you might have done a science experiment before, and there's a certain method and methodology that you follow in order to do a science experiment. In probability experiments, you're looking more at situations that have certain types of results. A very common example would be flipping a coin and getting heads or tails, or rolling a die and getting numbers 1 through 6, or picking a card from a deck and what are the odds of picking a specific value, a specific suit, etc. So in probability experiments, we're going to see a lot of situations that are like that. The outcomes are our possible results, come from the experiment. Now, an event is a subset or a sub-collection of outcomes. So let's think about an example. An example of an experiment might be, I'm going to take one die and I'm going to roll it. My outcomes are the numbers 1, 2, 3, 4, 5, or 6. So those are all my possibilities that could happen. Those are all my outcomes. Now, an event might be something like if I said I wanted to roll the die and get an odd number. Well, out of 1, 2, 3, 4, 5, and 6, the odd numbers are 1, 3, and 5. So I would have a 3 out of 6 chance of getting the event that I was looking for, or that simplifies down to 1/2. We represent probability as fractions. Your odds live between the numbers 0 and 1. It could not happen at all. It could have a 100% chance of happening, or my event could lie in between there. Okay, so in this example, if I said, what are the odds of me rolling a 7 on a die? The odds of that happening are 0%, 0. So we wouldn't say percent, we would just say that the odds of that happening, or the probability of that happening, is 0. If I asked, what's the probability of me rolling a 1, 2, 3, 4, 5, or 6? Well, that's every single option. So I would successfully reach that outcome and reach that or meet that event if I rolled any number on my die. And so therefore I have a 1 out of 1 or 6 out of 6 chance of that happening. So probability must live between 0 and 1. Now you're probably wondering what sample space is, because I kind of skipped over it. So sample space in probability is often marked with a capital letter S, and it represents the set of all possible outcomes. So with our die example, our sample space would be S equals 1, 2, 3, 4, 5, and 6. So if I said, I want my event to be rolling an odd number, you can see that that would be a subset of S, because my odd numbers are 1, 3, and 5. It's all coming back to what we did at the beginning of this session. So keep that in mind. Remember what a set is. Remember what a subset is. It's all going to come back. Now, empirical probability is actually the relative frequency of an event based on observation of an experiment. You can think of empirical probability being our experimental probability, in that you actually perform the experiment and see the results. That is very different from theoretical probability, which we are also going to look at. I'm going to erase some of the definitions above. Hopefully you've gotten that. You can always come back, right? But I want to do that so we can write down how we compute empirical or experimental probability. So I'm going to put that in a little cloud right here. And we would say that the probability of an event E happening is equal to the number of times E occurs over the number of times you performed the experiment. So before, when I mentioned the die and I said 3 out of 6, that was actually talking about theoretical probability, because I would assume that about or exactly 3 out of 6 times I would roll an odd number. That's what theoretical probability states. But if I were to do this as an experiment, I might say, I'm going to take a die. I'm going to roll that die. Let's make it a nice number that can be easily divided by 6. So let's say 30 times. So I'm going to roll that die 30 times. I'm going to keep track of what number I get each time. So let's say I roll a 1, I roll another 1, I roll a 2, roll a 6, I roll a 5, I roll a 6, 6, 3, etc. And I keep track of what I roll each time. To calculate the empirical probability, I would count the number of odd numbers I rolled, because that's the event E that I was looking for, and then I would divide that by the number of times the experiment was performed. So in the example I'm talking about now, that'd be divide that by 30. Now in a perfect world, we would assume that that would end up being 15 out of 30, because half of the numbers on the die are odd. But in experimental or empirical probability, that doesn't always necessarily happen. Let's look at an example. We have at a music store in New York City, 46 people entering the store were selected at random and were asked to choose their favorite type of music. Of the 46 people, 12 chose rock, 10 chose country, 4 chose classical, and 20 chose something else. So our sample space, S, is going to equal the set of responses. So that's rock, country, classical, and something else. Okay, that's my sample space. We're going to find the empirical probability for each of these. Now, this is empirical because it's based on an experiment. We asked 46 people, so our N, or number of people surveyed, is 46. So that's the total number of outcomes that we have. Okay, then we have our empirical probability will be the number of times each of these occurs. So the empirical probability that somebody says that they favor rock would be 12 over 46. The empirical probability that somebody favors country would be 10 over 46. For classical, the probability that they prefer classical would be 4 out of 46. And prefers something else or favors something else is everybody else, 20 over 46. Now, these are fractions, so we can simplify each of these fractions. Let's do so. When we simplify fractions, we look for a number that can divide evenly both into the numerator and the denominator. So here, the biggest number that goes into 12 and 46 is 2. The reason why this is important is your homework might tell you to simplify your probabilities and simplify your fractions. You need to make sure you can do that. So I get 6 out of 23. Here, same thing, 2 is the biggest number. That gives us 5 out of 23. Same thing here, 2 is the biggest number. And we end up getting 2 out of 23. And here, 2 is the biggest number. So divide top and bottom by 2. And we get 10 out of 23. Okay, those are our probabilities, our empirical probabilities for each of these examples. So let's look at a second example. We have several friends went fishing and caught 55 fish. The table below provides the details. So we have the fish and the number caught. We want to identify the sample space. The sample space is the set of all outcomes. So that's going to be grouper. And I'm not a fisher lady, a fisher woman, I guess. And so if I say a fish wrong, I apologize. Shark, I can say correctly. Flounder, like from The Little Mermaid, and kingfish. The only one I'm worried about is grouper. But you'll let me know if I said it wrong. That is our sample space. We're going to find each empirical probability. Now remember, the total number of outcomes in this experiment is 55. That's the experiment was essentially run 55 times. Is this fish one of these four? Yes or no? Which one does it belong to? That's our experiment. And we have our results. So the probability that we have a grouper, it happened 13 times out of the 55. That fraction cannot be simplified. One easy or nice hint for why it can't be is because 13 is prime and 13 does not go into 55. And so therefore it cannot be simplified. All right, the next one for sharks, I have the number of outcomes that were sharks was 20 out of the total number of fish in the experiment, which is 55. This can be simplified. Both of these are divisible by 5. If you don't know your divisibility rules, you might want to hop in on that and look it up. Come on, show up for me. All right, divide both of those by 5 and we get 4/11ths is our probability of having a shark. For a flounder, it happened 3 times out of 55. Again, 3 is prime and it does not go evenly into 55, so that one is fully simplified. And then we have kingfish. The probability of having a kingfish is 19 out of the total number of fish in the experiment, which is 55. 19 is prime and cannot go into 55. Therefore, that one is also fully simplified. So our answers are each of these. Okay, let's look at one more. Let's consider example 1. If I add up all of these probabilities, the probability that they favored rock, the probability that they favored classical, the probability that they favored country, and the probability that they favored something else, let's see what that adds up to. Those fractions. Now all of these had simplified down to 20/3, so I'm going to use the fully simplified ones. In the second example, I'm going to use the non-simplified ones because they have a common denominator. When we add fractions, we need to have a common denominator. So here we have common denominators, so I can just add the numerators up. 6 plus 2 is 8. 5 plus 10 is 15. 15 plus 8 is 23. So 23 out of 23, that adds up to 1. Okay, let's do the same thing with the grouper, flounder, shark, and kingfish probabilities. When we add up all of these fractions, again, there's a common denominator. Remember, I'm using the non-simplified one for the sharks. Let me double check. Yes. So when we add all of these up, I get 55 55ths, which is the same thing as 1, because any number divided by itself is 1. So the sum of the probability of all possible outcomes is always equal to 1, because if I add up all the possibilities, then that adds up to 100% of what could possibly happen, which as a fraction would be represented by the number 1. So let's answer some questions about these. What is the probability of an event that is certain to occur? That's going to be 1. What is the probability of an event that cannot occur? That's going to be 0. So let's say with the fishing example, you were fishing in the ocean and you asked the probability that a freshwater fish was one of the fish. Well, that's not going to happen because the ocean is a saltwater body of water. So that was not going to happen, or it shouldn't happen in nature. And so the probability of that happening would be 0. So the probability of an event must be between those two numbers, and they can be equal to. So my previous writing of it, when I wrote 0 is less than n, which is less than 1, we actually need to say less than or equal to, because it could be 0. The odds could be 0 that something happens, and the odds could be a 1 that they happen. The probability of A plus the probability of not A will always add up and equal to 1. Because if you think about it, the probability of something happening and the probability of something not happening has to be all possible outcomes. And so therefore that will be equal to 1. And if we have the probability that you win the lottery is 0.000008, what is the probability that you won't win the lottery? So we would take 1 minus 0.000008, and we would end up with 0.999992. So pretty much the odds are totally against you to win the lottery. I think we all kind of know that, but we can talk about that another time if you're interested in my take on that. But if we're trying to find the not something happening, and we know what the probability of it happening is, then we can always take the total possibility, 1, and then subtract the probability we know to get the not probability. Let me try and write that. So this is the total odds, right? The probability of an event that is certain to occur. So that's everything that could possibly happen within that experiment. If I take away the probability of it happening, the probability of the event, that will give us the probability of not the event happening. This is longer than I wanted it to be, so I'm going to go ahead and stop now and then make part 2 of this video on probability. Please make sure you watch that. It's hopefully not going to be as long, and I promise to try not to go over so many examples. If you have questions, always let me know, but make sure you watch the next video.